Okay, so we have a hypothesis test here, but instead of a mean, we're dealing with a proportion. Now, one thing to note is that when we are dealing with proportions, we don't need to worry about that whole z-t decision. We're just going to go to z because some mathematical reasons we won't go into right in this particular video. Um, so the proportion here of students, college students who say they're interested in election results is 65%. And we have a political scientist who thinks that theirs is more than 65%. And so we have a sample within that district's results, and then we have our level of significance here. So just to make it clear what's going on here, we have the null hypothesis proportion here of 65%, but the idea is this political scientist claims it's actually higher over here. So in order for us to reject this null and kind of agree with this political scientist, we're going to put 10% chance of error right there on the right side. It's going to be a right tail test. Now we don't know what this cutoff is yet. That's our critical value. But let's go ahead and take a look at what's going to happen here. So the null hypothesis, remember, will always have an equal sign. And here we're dealing with a population proportion. This is a sample proportion. The null and alternative are always focused on the population. And remember, null is nothing, so this would be 0.65. If there really is nothing different about this other district, the should be 65% of the college students there are interested also. Now here, remember that the parameter is going to stay the same and the number is going to stay the same, but the symbol is going to be different. And here, remember that the claim is that these results are more than 65%. This is the Q that lets us know we're looking at the greater than sign, that phrase more than. Okay, type of statistic to use. We're going to use a z for our proportions. Value of the test statistics. So let me pull up a Jamboard here. You remember this formula that we've had quite a bit from original normal distributions, and then we started working with sample means, and it was a very similar thing. Well, here we have the same idea. So we have z equals p hat minus mu of p hat over standard deviation of p hat. But we can simplify a couple of these. So the average of the p hats is just the null hypothesis proportion. And this one right here, a little more complicated. P times 1 minus p all over n. So that standard error there is a little bit different. But that's the formula we're working with. And notice the repetition in all of these. It's just whatever you're measuring, that's going to kind of determine the other two values. You're standardizing this relative to the rest of whatever this thing is. All right, so the value of the test statistic, let's grab our calculator and follow that formula I just put in. So we're going to start off with our p hat, which is, oh, we never actually got that. That's 195 divided by 275. So whatever that is, that's our sample proportion. We're going to subtract our null hypothesis proportion, and then divide by, let's do the square root after, I guess. So we're going to do p 0.65, make sure we get enough parentheses in here, times 0.35 divided by the sample size here, which was 275. And then all of this needs to be packaged in a square root. So not the easiest formula to do. Do want to make sure that you're checking that out closely as you're putting in. But that gives us our test statistic. Now, is the test statistic far enough? Well, what's our critical value? Remember we said that we want the value here, the z-score, that would give us 10% to the right. And that's exactly what the ALEKS calculator does when we put in this z right here, and if we put in 0.10, this will give us the z-score with 10% to the right. So remember, somewhere in your notes, you should have that very clearly marked, what each of these 4 buttons does on the ALEKS and which direction they give you. So this, whatever number we put in here, that's the portion to the right of the z-score that we're going to get out of the calculator. And that z-score happens to be 1.282. So if we go back to our image here, that cutoff there, right down here, was, sometimes I put a star, equals z point, what did I just say, 282. 1.282. So as long as our particular test statistic, when we go through this calculation right here, as long as that is further out into the tail, we're going to be inside the rejection region, and we're going to reject the null hypothesis. And in fact, our 2.054 was well beyond that 1.282, so there is enough evidence to support the claim that it is more than 65. In other words, there's enough evidence to reject the null. We are in the rejection region. Our test statistic is in the rejection region, so we're going to reject the null and go with the alternate claim, which is that this district is higher than that 65%. Okay.